Okay, so this morning, let's finish up the vibration. We have like 2 slides left on this one. But this was what we had for Gaussian, and I talked about how they have a strange scientific notation in Gaussian. So it's 0 point something, and then that D plus 04 represents times 10 to the 4th. Okay, maybe you've seen E. Like sometimes, yeah, in programming you can use E plus 04, and Excel will actually read that in. So if you want to type in Avogadro's number, you can type in 6.022 capital E plus 23, and it'll understand that. So that's kind of handy sometimes. If you want to type in a big number, you like 1E9, and boom, Excel will put in a billion. So so to put these, again, expand those numbers, these are the partition functions that we have calculated using Gaussian, and we were able to calculate these from their rotational constants and the translational motion. But notice the vibration V equals 0 and electronic are both 1. Why is that? Let's review just a little bit. Why is this? We haven't talked about electronic, but why is vibrational 1? We have 3 vibrational motions in this molecule. Okay. How many total? Well, we have 3 vibrational motions. So this is telling us that each one of those, because the total partition function is each partition function piece times all the others. So it's partition function for rotation 1 times rotation 2 times rotation 3 times the translation, really 1, 2, and 3, but those are all gathered together, and then times vibration 1, vibration 2, vibration 3. So this is all 3 vibrations. Each one of those is only, the partition function is 1. So that tells us they're all in the ground state, right? And there's not enough temperature to excite those to even the first level. And so this is, again, the total partition function is the product of all those individual partition functions. And so if you took the rotational, which is 2228, times the translational, which is looks like 14 billion, times 1, you get 33 billion. So that's a rough count of how many energy levels in this molecule are populated. And it also tells you that you're up in the range where, you know, it's really easy to add more energy level. Like if I add a little bit of energy, there's plenty of energy levels for this to populate. It's the vibrational motion is probably not going to be populated, but the translational motion will be. And most of the heat that we have in a gas phase molecule is in translation. So this also kind of was confirmed by those the kinetic theory of gases, that basically the gas is flying around, that's where the heat in a gas is. It's in the kinetic energy of the molecules flying around in space. We can kind of see that. That's the largest component of our transition, of our partition function. Where, remember, the partition means how we partition the energy in a molecule. And so most of the energy is partitioned into the translational motion, quite a bit in the rotation. So those are going to interchange with each other. You hit a molecule and it's going to spin more, or if a molecule is spinning and it hits another molecule on the end, then it'll give that molecule more translational energy. And so let's talk about the electronic motion. It was also 1. So we're in the ground electronic state. And notice that delta E, the homoluminal gap, is typically the smallest gap in the molecule. And those are huge, okay, in terms of temperature. So since we're in the ground state electronics excitation, that's going to be E equals 0 for the electronic state as well. So our ground state energy will be the 0 energy for the molecule. So it'll be the ground electronic state, the ground vibrational state, the ground rotational states. All of those will be set to 0. So if the molecule has those lowest quantum numbers in all of those, then that's defined as 0. So we're not adding any energy to the molecule from the electronic excitation because the electronic energy's in the ground state. And so if the molecule has a doubly degenerate ground electronic state, like nitric oxide, so NO, has that unpaired electron, and it can be in the px orbital, the py orbital, you know, in that molecule, the pi orbital in the xz plane, or the pi orbital in the yz plane. That's going to be a degenerate ground state. And so it would have an electronic partition function of 2. But that's a pretty rare case. Most other molecules have a singly degenerate ground state in terms of their electron cloud. And so the partition function for the electronic portion is going to be 1. Now, why would it not be excited at room temperature? Well, think about this. If, like in the visible region, a really low HOMO-LUMO gap would be a wave length difference of 700 nanometers. You know, there'd be an absorption down in the red. Most of our organic molecules absorb in the UV because they're colorless. They don't see any color visibly. They start turning yellow, like if you nitrate a molecule, it starts to turn yellow. That's because it's absorbing in the blue. But you get an extended pi cloud or something like that, then you might get that peak to move out down into the red region. So for an extended pi cloud, a small HOMO-LUMO gap, you might have a lambda max at 700 nanometers. So what kind of temperature would it take to excite that molecule up to 700 nanometers? So let's convert that to wave numbers, and it's 14,000 wave numbers. So comparing that to Boltzmann's constant, dividing by 0.695 gives us temperature, and that's 20,000 Kelvin. So you'd have to get that molecule to be excited electronically, just thermally, excite the electronic energy levels with heat. You'd have to have a temperature of 20,000 Kelvin. And the molecule's not going to survive that. So you really never have any thermal contribution in the electronic motion. So when we talk about the degrees of freedom in a molecule, we're only talking about the atoms, the nuclei, right? 3n minus 6 vibrations, 3 rotations, 3 translations. We don't count the electrons because they're not adding anything to the motion of the molecule where you could store energy, thermal energy. It would be a lot more complicated thermodynamically if we had to keep track of the electrons too and what they were doing in terms of our heat capacities, where we store energy. And so this is putting it all together. This is what Gaussian does when it calculates that total partition function. We have the translational piece over there on the left. We have the rotational piece in the middle. And then we have the vibrational piece. And notice the vibrational piece has 3n minus 6 terms. So this is for a nonlinear molecule. And so how many parts to the partition function? You have the translation, rotation, and then all of the vibrations. And they're all multiplied by each other. Now in terms of energies, it's the sum. So it's the energy of translation plus the energy of rotation plus the energy of vibration plus electronic. But for the partition functions, it's the product. Everything multiplied by each other. So that's a big distinction between energy and the partition function. What is it for the wave function? Remember when we were dealing with wave functions in the fall? Was it the sum of the vibrational wave function plus the rotation plus the translational wave functions, or plus the electronic wave functions, or was it the product? Since we're talking about all these different possibilities, it's the product. So the total wave function is the product of all the individual wave functions. We just take those wave functions and multiply them by each other. So the partition function is very similar to the wave function. In fact, it's trying to capture the behavior of the wave function. Okay, so let's review by taking a Kahoot over the rotation and vibrational partition functions.
Don't mind me.
Toss that back.
Usually just call it a day.
Yeah.
Yes. Yeah, well, I just want to make sure you get your money's worth.
Amen.
Right. College is the only place in the world that I've ever seen anybody pay full price for something, like get a shopping bag. You can go get, like you got a shopping cart, right? Let's say it was a single price for the whole shopping cart. And then you go through the store and you only put just the bare minimum in there. If that was really like a shopping thing, $100 for a shopping cart, you fill it. Whatever you walk out with, if it's in that shopping cart, you get to keep. That thing would be mounded over. You'd be doing like I do at Yummy Yummy, where you stick the snow peas in there and you extend the bowl up, and then you can put even more in there, But in college, no. Oh, I don't want any more than that. Isn't that weird? It's really weird. Yeah. I know. It's so strange. It's just an observation. Yeah, so let's now take this information, the statistical thermodynamics, and expand it into the thermodynamic properties, right? So we have a lot of those that you've heard of, enthalpy, entropy, and so on. Well, one of those that we've been talking about, I'll throw it in there a little bit, is called heat capacity. So I've been talking about heat capacity and how we store energy in a molecule, and it's related to this. So, yes.
It's not on the.
Thank you. Thank you. That's why they're pointing at the screen. I do not get mad when you point out my mistakes. It makes us better. Okay. Is it working? Yes. Okay. So internal energy, we'll do that first, and we'll expand upon that next time. But today we'll mostly focus on heat capacity. So this is the part of statistical thermodynamics. We've done the statistics part. We've done the probability, the first lecture, Boltzmann distribution, microstates, and units of an ensemble. So like a mole of molecules would be an ensemble of identically prepared systems. So that just means the molecules are indistinguishable. And then we connect these quantum counting statistics to bulk properties using information or terms that we're familiar with. Energy, entropy, enthalpy. Helmholtz free energy might be new to you, but you've heard of Gibbs free energy. Okay, so and then heat capacity and equilibrium constant. So we'll go all the way through this in the next couple of lectures to where we'll derive the equilibrium constant based upon these statistical methods. And today we're talking just about the energy and the heat capacity. So we're focused on those two in this lecture. So the internal energy. So if we take that Boltzmann distribution and we have the probabilities of each of those states, what we have here is the probability. This piece here is pi, probability of being in energy level I. And since that's our probabilities, we could multiply that by a figure of merit, something we're interested in. Remember the dart game? Our interest was in dollars. We had the probability of hitting a green, a blue, or a red area, but we really weren't interested in red, green, and blue. We were interested in money. So we paid $5 to play or $2 or whatever it was to play the dart game. I think it was $2 to play? Yeah, I can't remember the example. But the red was $5 back. We thought, hey, we might win $5, And then the green was $3, and then the blue was $0. And it turned out that the expectation return was going to be $1.22. Okay. So we were going to lose money. Well, in this case, we're not interested in money. We're interested in energy. Now, later on, energy turns into money. Okay. When we get to the last part of the course, we're talking about we pay for joules. When you go to the electric bill, it says kilowatt hours. Well, a watt is a joule per second or joule per time, and then it's times time. So you're paying the electric company for joules. So they generate joules and you buy them. So we're buying units of energy. So let's not get down that road. But anyway, we have the probability here, and we multiply by the thing we're interested in, the energies. So we have the energy of the ground state, the first excited state, the second and third, and so on. And when we sum those together, we get the expected energy, or the average energy, and we call that the internal energy. And so at this point, we have a decision point. I was looking back through the notes after many years of teaching this, and I realized we have really two ways to calculate this internal energy. There's two equations. And that was confusing for the students. Do I use this one or do I use that one? And in this case, notice that we have a summation. And we have a partition function, which is also a summation. And so you can really only use this energy equation if you have a countable number of levels. Right? So if it's a 2-level system or a 3-level system, or for goodness sakes, a 5-level system, something that you really have a hard time doing by hand, but still it's a countable number, then you would use this equation. But when we start talking about a mole of molecules at room temperature, 33 billion energy levels, that's not a countable system. No one's going to assign that to you, okay? So you would not use this equation for internal energy for that kind of system. Okay, we'll look at that equation here, probably either today or the next time. So this is the first one we started with, was the summation of the Boltzmann factors to create the partition function, And then the summation of the probabilities times the energies gives you the expectation energy or internal energy. And so, so from this internal energy and the partition function, you can calculate all the other thermodynamic properties. And so here's the equation for entropy. And big flashing star means this is note card bait. Okay. So these equations. We'll develop the entropy a little bit more detail later, but this is just showing you where we're going with this. And notice that the entropy is related to the number of energy levels populated. That partition function. And in all of these cases, we're dealing with, we'll deal with energies. Like in this case, we've got, instead of Boltzmann's constant, we've got the gas constant. But let me show you something that might blow your mind. So we have Boltzmann's constant in joules per Kelvin, okay? And what if we wanted to work in joules per mole? How would we convert that to joules per mole?
I bought the culture.
Think about the new units. You could divide or multiply. But what is the units on Avogadro's number? It's things per mole. So we want to keep that, so we multiply. Okay, so 6.022 times 10 to the 23rd per mole. So I'm just put mole minus 1. I can put that. Can someone do that real quick on the calculator? And notice the times 10 to the minus 23, times 10 to the plus 23. Yeah, those are going to cancel out. So it's pretty easy. 8.31. 8.31 joules per mole Kelvin. Where have I seen that before? That's R. Yeah. So a lot of times students say, well, this equation has R in it, but in the notes or in the book it has K, Boltzmann's constant. And it's just different units. It's the same thing. So you've been using Boltzmann's constant your whole chemistry career, from freshman chemistry to the present. And it's pretty cool, especially dealing with gases. Because again, Boltzmann, his whole breakthrough was the kinetic theory of gases. And so that R, the gas constant, really should be called Boltzmann's constant. Okay? Because that's what it is. It's just different units. So this is equal to R. So whenever you're dealing with wave numbers, then you might use the 0.695 wave numbers per Kelvin in this equation. If you want to deal in joules per mole, use R. If you want to deal with joules, then just, like joules per Kelvin, just use Boltzmann's constant K. So you have the freedom to choose the units that you're going to use, but you just have to be consistent throughout. So if I calculate the internal energy in the top equation with wave numbers, okay, then I need to use R in wave numbers per Kelvin so that the internal energy and the gas constant have the same units, okay? And so then if we get the internal energy, we can also calculate Helmholtz free energy. And Helmholtz free energy is in situations where you have constant volume, but we don't like to heat sealed containers in the university labs. We do that in industry all the time because we can handle the pressure. So they'll put a 300-gallon reaction vessel together and it's bolted down and they'll heat that thing up and it's closed. And they'll monitor the pressure. But we don't like to do that because we use glassware. It's cheap, easy to clean, you can see through it. Okay, so we like glassware, so we do everything at constant pressure, and that's the, so the enthalpy, I'm sorry, I messed up. The enthalpy is enthalpy. This is the Helmholtz free energy, A, and then the Gibbs free energy, G. So hopefully I didn't confuse you. I got ahead of myself because of the writing from last year, which I tried to do. Okay, so we have USHAG, that's my acronym. So the internal energy, entropy, the enthalpy, which is H, the Helmholtz free energy is A, And again, that determines spontaneity in systems of constant volume. And then the Gibbs free energy tells you spontaneity in systems of constant pressure. And they both use the entropy. So we can calculate the enthalpy of a system, of a molecule, and if we have that molecule in reaction, it can be a reactant and it can react, and then you can have the enthalpy of the products, and you can have a delta H, so enthalpy of reaction. You could have a delta G. If you knew G for the reactants and G for the products, you could calculate a delta G. So that's what we did in Gaussian a few times, and we'll certainly do that more in this course in the lab. We'll calculate some molecules, calculate Gibbs energy for those molecules, and then look at delta G's for the reaction. Okay. And so then at high temperatures, remember we saw some really dramatic simplifications for rotational partition functions and so on. And so this energy for translational motion simplifies to 3/2 nRT. So it's just gas constant times temperature. If you think about the gas constant, takes temperature and turns it into joules per mole. And that's how much internal energy you have. So this is the equation you would use when you don't have a countable number of energy levels. Right? It's still internal energy. So then we have the internal energy for the rotation, and then vibration as well. But vibration's a little tricky. So we call this equipartition, high temperature. We have translational motion, and now it's just gas constant times temperature. The 3/2 is just in there. Again, that's the classical result of objects flying around in 3 dimensions. Same thing for rotation. Now for linear, we have 2/2 nRT, and it's the number of moles, so this gives us joules. Okay, and then the vibration. So whenever temperature is around 10 times the vibrational temperature, we have 1 unit of nRT for every vibration. So there should be 3n-6 of these. But we are almost never that high in temperature. In fact, for small molecules, you will never really take into account the vibrational energy component. Everybody catch that? For small molecules, because the vibrational energies are so high. Even a water, the HOH bend is 1,500 wave numbers. And room temperature, we have 200 wave numbers. Okay, so we're not going to get that motion to be excited. And so for water, we don't have any contribution of the vibrations to the internal energy. It's all translation and rotation. And so this is the other decision point. If you see equipartition, or if you're dealing with moles of molecules, these are the equations that you use. If I say a 2-level system, you don't use this equation. You use the individual calculations of the probabilities of being in each of those levels, and you calculate the internal energy. Now, if we take this change in internal energy with respect to temperature, that's the definition of heat capacity. So how much energy do I have to put in before the temperature moves? It's the slope of energy with respect to temperature. Well, these are pretty easy to calculate. What's the slope of each one of those equations with respect to temperature? It's temperature to the first power, right? So it's just the coefficient of that. So it's 3/2 nR for translation, 3/2 nR for rotation, and just nR for vibration. And that's called the heat capacity. So the equipartition heat capacities are very simple. So again, we don't have electronic components because we don't have electronic excitation. And so these heat capacities are given here. Is that derivative of the internal energy with respect to temperature, constant volume, and so the derivatives of 3/2 nRT with respect to T are 3/2 nR. And then notice down here is the number of active modes. So you could have up to 3n-6 there, but you almost have zero. You have 0 on most molecules. Like water, it'd be 0 active modes. To activate that mode, you need to be at 10 times the vibrational temperature. And that's just not going to happen. Okay. And so, but next time we'll practice calculating the heat capacities for various molecules. And there's some problems like that in the homeworks. And so here Gaussian calculates these as well. You have this in the Gaussian calculation output. 3/2 NR for translation, 3/2 NR for rotation, and then it adds up all of those vibrational components, and most of them adds up to 0 because we don't have active vibrations. Okay. Now this is just showing you that as you heat it up, as you heat up a molecule, you know, you start out here, you have the translational heat capacity, and then as you get close to those rotational temperatures, you start to see the heat capacity jump up. This is for a linear molecule, a diatomic. And then if you were to get hot enough for the vibrations, then it would jump up another 2/2 RT. But then eventually the molecule, if you're trying to excite it electronically, the electrons go to antibonding orbitals and the molecule dissociates. So what does it mean to excite the molecule electronically? You're going to move electrons to antibonding orbitals, and the bond order is going to go to 0, and the atoms are going to come apart. And now you have a separate situation. You don't have rotation, you don't have vibration, you have free atoms. So now you have 2 free atoms. Each one of those has a 3/2 NR. Okay, so it's 6/2 NR or 3. And so you get up here to this, you know, adding in this vibrational component, and then it dissociates, and then you end up with 2 free atoms. Okay. So that's what happens if you were to try to excite the electronic portion and store energy. Realize what we're doing is as we heat the molecule up, we're giving energy to the molecule. It's storing that energy for us. We can pull it back out with the expansion and so on. So all of our heat engines use this internal energy. We heat up a molecule, and then we use it to push a piston. When it pushes the piston, it cools down. And then we heat it up again, and we push a piston, and it cools down. And so now in our automobiles, we push the piston, it cools down some, and then we throw that gas away, and we bring in more gas and burn it. So how we heat it up is by burning it. Okay, but a steam engine, you know, we have a boiler, we're boiling that steam, making steam, it goes in, pushes the piston, cools down, and we throw it out. Okay. We could recycle it. We'd have to sink even more heat if we recycle it. And so we can calculate these next time because we're out of time.